In the last video, I showed you why you study 8 hours and learn nothing. I diagnosed the problem. Traditional methods create the illusion of knowledge. Several of you commented, "Okay, I understood the problem. But what about the solution? How do I actually do this in practice?" Today, I'm going to answer by doing, not talking. I'm going to take a concept I don't fully master. I'm going to study it here with you using my method. And you're going to see exactly what goes through my head. No cuts. No pretending. You'll see the mistakes, the gaps, the corrections, the real process. By the end of this video, you won't just know the technique. You'll have seen it working mentally. And then, you'll be able to test it with anything you need to learn. Let me give you some context. When I was at MIT, I noticed something strange. I had colleagues who could recite entire textbooks. They knew every formula, every definition, every theorem. But when you asked them to apply those concepts to a new problem, they froze, completely froze. And I realized they knew the names of things, but they didn't understand the things themselves. That's when I started developing this method. Not because I was smarter than them, but because I refused to fool myself into thinking that memorizing was the same as understanding. This technique took me from being a good student to winning a Nobel Prize in physics. Not because it's magic, but because it's honest. So here's what we're going to do today. I'm going to teach you the 4 steps of this method. Clear, structured, no confusion. Then I'm going to use those steps right here in real time to learn something I don't fully understand yet. You're going to watch my brain work. You're going to see where I stumble. And at the end, you're going to do the same with something you're studying. Let's start. Step 1, choose a specific concept. This sounds simple, but most people get it wrong right here. You can't choose quantum physics. That's not a concept. That's a field. You can't choose mathematics. That's not specific enough. You need to choose one delimited concept. Why do electrons jump between orbits? That's specific. How does photosynthesis convert light into energy? That's specific. Why does dividing by a fraction invert and multiply? That's specific. Think of it like choosing an ingredient to cook with. You pick one ingredient, not the entire grocery store. And here's the trap. The concept can't be too broad, or you'll get lost. It also can't be something you've never encountered before. This technique isn't magic. You need to have studied the material at least once. You need raw information in your head. What this method does is transform that raw information into real understanding. So wrong example, I'm going to learn mathematics. That's absurd. Correct example, I'm going to understand why the derivative of x squared is 2x. See the difference? One is impossibly broad. The other is one specific piece you can actually chew completely. I always did this. When I was learning physics, I didn't try to understand electromagnetism all at once. I took one tiny piece. Why does a changing magnetic field create electric current? Just that. I chewed on it completely until I understood every layer. Then I moved to the next piece. That's how you build real knowledge. Piece by piece, not trying to swallow the ocean. Step 2, explain it like you're teaching an 8-year-old child. This is where the magic happens. Why a child? Because a child doesn't accept jargon. A child doesn't pretend they understood when they didn't. A child keeps asking why until they reach the root. And that forces you to reach the root. You can speak out loud, you can write, you can record audio. The medium doesn't matter. What matters is that you verbalize it, not just think it, speak it. There's neuroscience behind this. When you explain something, you activate completely different brain regions than when you read or listen. You activate the prefrontal cortex, language areas, working memory. Your brain has to synthesize, connect, transform information into language another person can understand. That's high-level cognitive work. When you just reread, your brain is in passive mode. It's receiving information it's already seen, so it goes into autopilot. But when you try to explain, your brain has to work hard. And here's what's going to happen. You're going to freeze at some point. This is the goal, not a failure. The freeze exposes your gap. You thought you knew, but you don't really know. It's like testing a bridge by walking on it. You don't know if the bridge holds until you step on it. You don't know if you understand until you try to explain. When I was teaching quantum physics to freshmen at Caltech, I never used an equation in the first class. I explained everything with balls and springs and everyday objects, not because they were stupid, but because if I truly understood it, I could simplify it. If I couldn't simplify it, I didn't understand it well enough. There's a story I love. When my son was 8 years old, he asked me how magnets work. I could have said magnetic fields and electron spin alignment, but that's not explaining. That's naming. So I spent an hour explaining it using only things an 8-year-old understands. Invisible hands that push and pull. North Pole and South Pole, like two kids who either want to hug or want to run away from each other. By the end, he understood magnets better than most high school students. And I understood magnets better too, because I had to rebuild my understanding from scratch to make it simple. Step 3, identify the gaps. This is where you freeze. This is the map. Most people ignore the freeze and keep going. Fatal error. The freeze is telling you exactly where to study. You have to go back to the material and study specifically that gap. Not reread everything. Go straight to the hole. How do you identify a gap? Where did you use jargon without explaining the jargon? Where did you skip a logical step? Where did you say it's like, but didn't actually explain the like? Here's a technique. Record your explanation and listen back. The stumbles become obvious. You'll hear yourself say, well, basically, and then mumble something unclear. That's a gap. You'll hear yourself use a technical term and then immediately move on without defining it. That's a gap. I was brutal with myself about this. I didn't accept. I sort of understand. Either I understood or I didn't. There was no middle ground. I have a principle. The first rule is that you must not fool yourself. And you are the easiest person to fool. Your brain is constantly trying to trick you into thinking you know more than you do. It's a survival mechanism. Your brain hates uncertainty, so it fills in the blanks automatically, even when those blanks are actually holes in your understanding. The gap is your brain trying to con you. This technique exposes the con. Step 4, simplify and use analogies. After you identify the gap, you reconstruct the explanation. You use everyday analogies. You compare the complex with the simple. You remove jargon, or you explain the jargon before using it. The goal is an explanation so clear that an 8-year-old would actually understand it, not just nod politely. Actually understand. How do you create good analogies? You take something abstract and find a physical or visual equivalent. Electricity is like water in pipes. Voltage is pressure, current is flow. Resistance is the width of the pipe. Is this a perfect analogy? No. Is it a useful analogy? Absolutely. A child can now visualize what's happening, and visualization is understanding. Here's the complete cycle. Explain, freeze, identify gap, study gap, rebuild explanation, test again. You repeat until the explanation flows without stumbles. It's like sculpting. You remove what's extra until only the essential remains. When I was learning any new area of physics, I always reconstructed everything from first principles. I didn't accept authority. I didn't accept it's this way because the textbook says so. I needed to understand why, and the only way to know if I understood why was to try explaining it simply. There's a story about this. When I was working on quantum electrodynamics, I invented my own mathematical notation, not because the standard notation was wrong, but because I needed to be absolutely sure I understood the foundation. So I rebuilt the entire thing from scratch using diagrams that made sense to me. Those diagrams later became famous as Feynman diagrams, but I didn't create them to be famous. I created them because I refused to use tools I didn't fully understand. I had to rebuild the house to make sure I knew where every nail was. All right, now we get to the practical part. I'm going to choose a concept to demonstrate this method live. The concept needs to be interesting, understandable for a general audience, and something I don't completely master. I'm going to choose, why is the sky blue? I have a general notion. Light scatters, shorter wavelengths, something about particles in the atmosphere. But I've never stopped to truly understand the mechanism. I studied the basics before recording this. but I didn't memorize. I want you to see the real process of transforming information into understanding. Here's what's going to happen. It won't be perfect. I'm going to freeze. I'm going to use the wrong word. I'm going to have to go back and correct myself. This is intentional. I want you to see that freezing isn't failure. It's part of the method. Pay attention not just to what I say, but to how I think when I freeze. I'm going to do the 4 steps here. When I freeze, I'll pause and point it out. Look, I froze here. This is the gap. Then I'll go back. Study the gap and try again. At the end, you'll hear 2 versions, the stumbling version and the fluid version. The difference will be obvious. Let me recap the 4 steps quickly. Step 1, I chose the concept, why is the sky blue? Step 2, I'm going to explain it like you're 8 years old. Step 3, when I freeze, I'll point out the gap. Step 4, I'll simplify until it's crystal clear. All right, enough theory. Let's do this. Okay, imagine you're an 8-year-old child and you ask me, why is the sky blue? Let me try to explain this. So sunlight looks white, right? But actually it's a bunch of colors mixed together like a compact rainbow. These colors are waves. Blue light has tiny waves like little ants. Red light has big waves like dogs. When this light enters the layer of air around Earth, it passes through millions of tiny particles. For the big waves, the red ones, these particles are like grains of sand. They pass right through. But for the small waves, the blue ones, the particles are like obstacles and they what? They bounce, they scatter. Okay, I'm freezing here. Look at what just happened. I used the word scatter, but I didn't explain what scattering actually is physically. An 8-year-old doesn't know what scattering means. That's gap number 1. Let me keep going. So the blue light scatters everywhere. And that's why when you look at the sky, you see blue light coming from all directions. The red light, it passed straight through and went far away. That's why sunset is red, because the blue light already scattered completely and only red is left. I'm freezing again. I just said blue light scatters more, but I didn't explain why it scatters more. What's the actual mechanism? Why do small waves hit particles and big waves don't? That's gap number 2. And I used this ant and dog analogy, but I didn't really connect it properly to the physics. That's gap 3. So let me map these gaps clearly. Gap 1, I didn't explain what scattering means physically. I need to understand the actual interaction between light, wave, and atmospheric particle. Gap 2, I didn't explain why small wavelengths scatter more than long wavelengths. What's the relationship between wave size and particle size? Gap 3, I don't have a good analogy for the scattering process itself. The ant and dog thing doesn't quite work. Now I'm going back to the material. I'm going to study specifically these 3 things. Not reread everything about light, just these gaps. So scattering. What I found, when a light wave hits a particle that's roughly the same size as the wavelength, it makes the particle vibrate. The vibrating particle then re-emits light in all directions. That's scattering. It's not bouncing like a ball. It's more like the particle becomes a tiny light bulb that glows in all directions. Now wavelength sizes. Blue light has a wavelength around 450 nanometers. Red light is around 700 nanometers. Atmospheric particles. The nitrogen and oxygen molecules are tiny, about the size of blue wavelengths. So blue light sees these particles as obstacles. Red light, with its bigger wavelength, basically doesn't even notice them. It's like throwing pebbles versus throwing bowling balls at a chain link fence. Pebbles get caught. Bowling balls go through. Now I need a better analogy. Let me try this. Scattering is like a sieve. Imagine you pour water mixed with sand through a sieve. The big things, pebbles, pass through the holes. The small things, sand grains, get caught in the mesh and fall everywhere around the sieve. Blue light is the sand, red light is the pebbles. Atmospheric particles are the mesh. Blue gets caught and falls everywhere. Red passes through. That works better. All right, let me try explaining again. Second attempt. Okay, imagine you're an 8-year-old. Sunlight looks white, but it's actually made of all the rainbow colors mixed together. These colors are waves. Blue light has short little waves, like ripples in a puddle. Red light has long waves, like ocean waves. When sunlight enters Earth's atmosphere, it travels through billions of tiny particles. mostly nitrogen and oxygen molecules. These particles are very small, about the size of blue light's waves. Here's what happens. When blue light with its short waves hits these tiny particles, the particle starts vibrating, like a tiny bell that got struck. And when it vibrates, it sends blue light out in all directions, like a little light bulb turning on. That's what we call scattering. The blue light gets redirected everywhere. But red light, with its long waves, is too big. When it encounters these same tiny particles, it's like an ocean wave passing over a small rock. The rock doesn't stop the wave. Red light just keeps going straight. So when you look up at the sky during the day, you see blue everywhere because blue light has been scattered in all directions by these atmospheric particles. It's coming at you from above, from the sides, from everywhere, red light. It went straight through and continued to the horizon. That's why sunsets are red. By the time the sunlight reaches you at sunset, it has traveled through so much atmosphere that all the blue has scattered away. Only the red light, which ignored all those particles, makes it through to your eyes. You see the difference? In the first version, I froze 3 times. I used jargon without explaining it. I didn't have the mechanism clear. I had a weak analogy. In the second version, it flowed. An 8-year-old would actually understand this. And here's the thing. I didn't become smarter between attempt 1 and attempt 2. The difference is that I identified the gaps, went back, filled them, and rebuilt the explanation. That's the method. Simple, yes, easy? Not necessarily. But does it work? Always. Most people stop at the first stumbling attempt and think, I can't explain this, so I don't understand it. Forget it. I thought differently. I can't explain this. Perfect, now I know exactly what to study. See the mental difference? One gives up. The other uses it as a map. And now, if you ask me again in a week, why is the sky blue? I'll remember. Why? Because I built this understanding, I didn't memorize it. My brain has the structure, not just the words. When I learned physics this way, I remembered concepts for decades. Knowledge you build stays. Knowledge you memorize evaporates. Now let me show you the patterns that appeared here. These patterns will show up in any application of this method. Pattern 1. You'll always freeze where you have a hidden gap. When I froze on scattering, it was because I thought I knew what it was. But I didn't really know. Your brain hides gaps from you. Explaining exposes them. Pattern 2. Jargon is a symptom of lack of comprehension. Every time you use a technical word without being able to explain it in simple terms, you have a gap. An 8-year-old doesn't know what Rayleigh scattering is. If you can't explain without using that term, you didn't understand. You just memorized the name. Pattern 3. Good analogies come after understanding, not before. I tried to create an analogy before filling my gaps. It didn't work. After I understood the mechanism, wave size versus particle size, the sieve analogy appeared naturally. An analogy isn't a magic trick. It's crystallization of understanding. Pattern 4. The second explanation is always radically better. The difference between first and second attempt isn't 10% better. It's 500% better. This proves the method works fast. Why does this work neurologically? Brief science. When you try to retrieve information from memory, when you explain, you strengthen neural connections, much more than when you passively review information by rereading. Creating analogies and explanations creates multiple neural pathways to the same concept. When you identify gaps, you activate metacognition, awareness of your own knowledge. You're learning to learn. Your brain learns by doing, not by watching. It's the difference between watching someone swim versus swimming yourself. Rereading is watching. Explaining is swimming. Your brain creates muscle memory of the movement, not memory of the video. This method works for any content. Let me give you examples. Medical students studying the Krebs cycle. Try explaining to an 8-year-old how the body transforms food into energy. You'll freeze. Where? On the enzymes you memorized the names of, but didn't understand their function. Go back, study those specific enzymes. Rebuild, done, you'll never forget again. Law students studying presumption of innocence. Explain to an 8-year-old why a judge can't assume someone is guilty before trial. Can you do it without using burden of proof? If you can't, you have a gap. Program a learning binary search algorithm. Explain to a child how a computer finds a name in a giant list superfast. Use the analogy of searching for a word in a dictionary. A child understands that. Someone learning about investments? Explain to a child what it means to buy a piece of a company. If you freeze on dividends, IPO, valuation, you have gaps. The method is the same, always. The content changes. The process doesn't. Here's the ultimate test. Can you teach it? If you can't teach something, you haven't truly learned it. Teaching is the final test of comprehension. You can fool a professor on an exam. You memorized, you cheated, you got lucky. You cannot fool an 8-year-old child. They immediately sense when you're talking fancy but not making sense. If you can't explain it simply, you don't understand it well enough. I practiced this principle religiously throughout my entire career. Now, before you do anything else, before you continue watching YouTube, before you do anything, you're going to do this now. Step 1, take a concept you studied this week, any concept. Step 2, open a notepad, turn on your phone's audio recorder, or grab paper and pen. Step 3, explain that concept like you're teaching an 8-year-old. Step 4, don't try to make it perfect. I want you to freeze. The freeze is the map. Step 5, when you freeze, mark where you froze. That's your gap. You don't need to fill the gap right now. You can do that later. I just want you to identify the gap. This alone will change how you study. Why do this now and not later? Logic, the more time you wait, the more you forget what you studied. Test it now while it's still fresh. Neuroscience, your brain is activated now. Take advantage of this state. Practical, it takes 3 minutes. You have 3 minutes. Emotional, if you don't do it now, you know you won't do it. Be honest with yourself. I wasn't someone who said, I'll do it tomorrow. I was someone who said, I'll do it now and see what happens. Scientific even about this. I tested immediately. If you did the challenge, comment, I froze at X. I want to know where you froze. If you discovered an unexpected gap, tell me. You don't need to explain the whole concept. Just say where you froze. This creates a community of practitioners. You feel less alone in the freeze. And the data in the comments is interesting. Patterns of gaps. At the beginning of this video, the Feynman Technique was just a name to you. Now you've seen it working in real time. You saw the 4 steps. You saw the freezes. You saw the difference between first and second attempt. More importantly, you saw that it works. It's not theory. It's practice. You don't need to study 8 hours and forget everything anymore. Now you have a method that transforms information into real comprehension. It's not about time invested. It's about how you invest that time. I wasn't a genius because I had an IQ of 200. Actually, mine was 125, just above average. I was a genius because I had a superior method. And this method isn't genetic. It's learnable. You just learned it. Now you know the method, but knowing isn't doing. There are 2 paths now. Path 1, you watch this video, find it interesting, do nothing. You keep studying the old way. In 1 year, same frustration. Path 2, you test today, you freeze. You identify the gap. You fill it. You see the difference. You never go back to the old method. Which do you choose? In the next videos, I'll show you how to use this method in specific contexts. Mathematics, programming, languages, each has its nuances. If this made sense, stay with me. There's much more. Next video, how to use the Feynman technique when you have little time. Most people use it wrong and waste time. What I cannot create, I do not understand. Now you know how to create understanding. Go